Good day, we are the Group 5 of CPE 107L Section B2, and this is our Project 1 vlog, which is a documentation of how we came up with an AHI counter or an apnea-hypopnea index counter with a 7-segment display in Logisim. And this vlog will be divided into 6 detailed parts to explain that whole process. So the first part will be the system analysis. In this project, we are asked to create a system using an adder and decoder which outputs the severity of sleep disorder. So the severity of sleep disorder is actually determined by the AHI count occurrence. So the apnea-hypopnea index count is actually a scale of measurement of how severe your sleep apnea is. So the higher the count means that you have a worse condition of a sleep apnea. So this system will also consist of 2 sensors, sensor 1 and 2, paired with a threshold value. And the condition is that whenever sensor 1 and sensor 2 values are greater than or equal to the paired threshold value, then it should increment the counter. It is shown in our table that for a certain range of AHI count, it should display a number in our 7-segment display. For instance, a 0 to 7 count should display a 0, and 8 to 12 should display a number 1, and so on and so forth. But how will we be able to implement the condition for the sensor and the threshold value? So for that, we will be creating a comparator, and then the output of that comparator will then be fed into our 5-bit incrementer, and that 5-bit incrementer's output will be fed into our decoder for our 7-segment display. So all of this will be discussed in detail. So starting from the truth table, there will be a K-mapping and a deriving of the Boolean expression, all in preparation for the Logisim circuit design. So the next part will be delivered by Sienna TARIMAN.
Alright, I am Sienna TARIMAN, and based on what we've seen previously, we now have an idea on the conditions required by the system as explained by Mads. So prior to implementing our decoder, we must first obtain its SOP or sum of product equations by means of a K-map derived from a truth table. Based on what we can observe on our screens, on our problem for the project, the AHI count is seen from 0 to 32. So since the count is up until 32, we can actually have its corresponding binary number. So since its count is up until 32, we can actually have 5 inputs because that will be 2 raised to 5, which will incur 32 outputs in total. But as we can see here, for each AHI count, its range, it will correspond to a certain decimal number that will be outputted on the 7-segment display, as we can see right here. So if we go over to our left side here, this is actually our truth table of our AHI count and the 7-segment display. So take this table over here. This is its corresponding truth table with 5 inputs, and then each output that we can see over here corresponds to a segment in our 7-segment display. So for our AHI count, range 0 to 7, we can just think of this as binary number 0 to 7. So this is 0 up until 7, as marked here. There is actually a border so that we can easily see it. So from 0 to 7, that range, the 7-segment display must be in 0. So taking a look at our 7-segment display over here, if we would want it to output 0 or mimic the number 0, the segments A, B, C, D, E, and F must be lit, while G remains unlit, so that it could output the number 0. So from 0 to 7 over here, A, B, C, D, E, and F segments are in 1 because we would want it to have a high signal so that it could be turned on. And then G from 0 to 7 will be 0 because we would want it to remain off. So for range 0 to 7, this is the outputs for the 7 segment. So it will be 1 1 1 1 1 1 0. And then up next for the AHI count 8 to 12 right here, then we would want it to output 1. So for our 7 segment display, if we would want our display to mimic the number 1, segments B and C should be the only ones in the on state. So if we would want that to happen here, we only want segments B and C to be on, so it should have a high signal, so it will be 1, while the rest of the segments will be off, therefore it's 0. So this is the same for counts 8 to 12. And then moving on, for AHI count 13 to 17, it would display the number 2 in our 7 segment display. So if we would want our 7 segment display to mimic the number 2 or decimal number 2, all the segments should be on except for segments C and F. So looking here again at our truth table, it is only C and F that are in 0 and the rest are 1 because we would want it to be on. So the same is true up until AHI count 17. So this is the output for 13 to 17. Then moving on, for AHI count 18 to 21, when it falls at that range, we would want the 7 segment display to display the decimal number 3. So again, looking at here at our 7 segment display, if we would want it to mimic decimal number 3, all the segments are lit except for segments E and F respectively. So if we would want that to happen, E and F should be 0, everything else is 1 because it is lit. So the same is true from 18 to 21 for the AHI count. So this is its corresponding cells for its outputs A to G. Then lastly, for AHI count 22 to 32, if it falls in this range, we would want the 7 segment display to output 4 or decimal number 4. Then looking at our 7 segment display, if we would want it to mimic the decimal number 4, the only on segments are B, C, F, and G. So if we would want them to be lit, they should be at 1. So if it would be B, C, F, and G, B, C, F, and G, those are the only ones that has 1. And then everything else, A, D, E, are at 0 because we would want them to remain unlit, while B, C, F, and G are lit. So the same could be said for 22 up to the very last here at 31 for the decimal equivalent. So this right here is the truth table for our AHI count and its corresponding 7 segment display. So from here, we will create a K-map for each of our outputs here for each segment. So there will be 7. And since we have 5 variables for our K-map, we will have 2 corresponding 2x2 matrix, in which the first matrix is when input A is equal to 0 and the second is A will equal to 1. So we will get right onto that after this. So moving further down, we have here our K-maps per output of each segment. So focusing our attention here to the leftmost side, let's not mind output B first. So based on the ones that we were able to get from our truth table, we just have to map out the ones here on our 2x2 matrix. And if we look closer, we can see that each cell corresponds to each of the binary row that we had. So for output A, we actually have 5 minterms in total. So for numbers 0 to 15 over here on our left matrix where A is equal to 0, our first group consists of 8 cell members, and since it was able to encompass all 4 columns, it inherently cancels out D and E. So what we're left with is not A and not B, because as we can see here, for literal B, the unchanged bit is 0, therefore we would have to invert B. And then up next for this group over here, we have not A, and then we have literal C because its unchanged bit is 1, so we don't invert it. C will stay as is, and so will literal E because its unchanged bit is also 1. Then for the next group over here, we also have not A because A is not cancelled out because we do not find any group of A overlapping with the matrix on the right side. So as we can see here, it will also be not A, and since the literal that remained unchanged was C and the unchanged bit was 1, C will stay as is. And then for the column, the unchanged literal is D and the unchanged bit is 1, so D will stay as is. So for the left matrix, we have not A ANDed with not B, ORed with not A, ANDed with C, ANDed with D, ORed with not A, ANDed, ORed with not A, ANDed with C, ANDed with E. Sorry, my bad. And then for the right matrix, up here on the top, since our first group was able to encompass all 4 columns, we effectively cancel out D and E. Then since it only occupies a single row, both the literals on that row will be included in our minterm. And since the unchanged bit for those 2 literals are 0, it will be 0, 0. So B and C are both inverted. So for this one, we will have A, not B, and then not C. Then for our last group over here, we have, for its row, we still have A because it won't be cancelled out. And then for the row, we still have B because the unchanged literal is B and the unchanged bit is 0, so we would have to invert B. Then for its column, the unchanged literal is D and the unchanged bit is 0, so we invert D. So once we have this over here, we can simplify it to this SOP equation by factoring out the common terms and then inherently ANDing them with the terms that are left. So from these 3 minterms, they have common of inverted A. So A, inverted A will just be ANDed with the terms that are left, and the inside there will all be ORed. And then for these 2 minterms, the common terms are A and not B, so they will be pulled out, and then it will just be ANDed with the ORed literals that we have left here on the inside. And then moving on to output B here on the right side, we can see from our truth table from a while ago that from AHI count 0 up to the very last, it was all actually 1. Therefore, all of our cells in our matrices are all 1. So they are gonna be grouped for its entirety, 16 members each. And then since this is a 5 variable K-map, we can think of this as a 3-dimensional output. So if that is the case, then they inherently overlap. So literal A also cancels out along with literals B, C, D, and E. So if all literals are cancelled, output B will just inherently be 1 or a constant. So moving on here to our lower side for output C, again, we have two 2x2 matrices, and we have 3 groups for our matrix on the left. So for our first group, it is actually the same as the one we had prior to output C, which is this group over here that has 8 members. So this will just be not A ANDed with not B. And then for our group here on our lower side, it will encompass all 4 cells down here and all 4 cells up here, making it an 8-member group. So A will still be there, it won't be cancelled out. But since it was able to encompass all columns, D and E will be inherently cancelled. And then since the literal that remained unchanged was C and the unchanged bit is 0, it will be not A ANDed with not C. And then for group number 3, we have it here. And since it was able to encompass all the rows, we inherently cancel out literals B and C. And since it only occupies 1 column, both literals D and E will be in its min term, and D and E will both be inverted because their unchanged bit both 0. So for this group, it will be not A ANDed with not D ANDed with not E. And then moving over here to our matrix on the right side, our first group is an 8-cell group, 8-member group. So it will be this one. So since it was able to encompass all the rows, it effectively cancels out B and C. Then the unchanged literal is D, but the unchanged bit is 1, so D stays as is. This will be A ANDed with D. Then next group is this one. It also inherently encompasses all 4 columns, so it effectively cancels out D and E. And the unchanged literal is C, and its unchanged bit is 1, so C stays as is. This group will be A ANDed with C. Then lastly, down here, also an 8-member group. It was able to encompass all 4 columns, so it effectively cancels out D and E as well. Then its unchanged literal is B, but the unchanged bit is 1. Therefore, B will stay as is, so it will be A ANDed with B. So putting all together our min terms, they will be ORed. We will come up with this SOP equation, but this SOP equation right here can still be simplified to this SOP equation. So taking in our first min terms, they all have not A or inverted A as their common literal, so we can factor that out. Then it will just be ANDed with the ORed min terms that we have left here, and then this will be effectively ORed with the last 3 min terms. But as we can see, the last 3 min terms have A that is common to all of them, so we factor out A, and this will be ANDed with the terms we have left here. So this is our SOP equation for output C or segment C. Moving on here to our right side for output D, as we can see here on our matrix to the left, our 2x2 matrix to the left, we have 3 groups. And then the first group, just like what we had prior to this, also in C, it is an 8-member group, and this will just be not A ANDed with not B. And then similar to what we have in A also, in output A from a while ago, these 2 groups, this one will be not A ANDed with not C ANDed with E. Then this group is not A ANDed with C ANDed with D. And then similarly also from output A, we have this group right here, which is a 4-member group. And then this group will just be A ANDed with not B ANDed with not C. And then this group will just be A ANDed with not B ANDed with D. And for output D, it's actually similar to our output A. So this is our SOP equation for output D. Moving on to output E. Over here, we actually have tons of zeros as compared to the ones we had before this. So as we can see on our left matrix, its matrix cells are actually very, very similar to the left matrix of output D as well. So this group right here on the top most, it's 8-member group. Again, it is just not A ended with not B. This group here in the middle, a 4-member group, it is just not A ended with not C ended with, it is not A ended with C ended with E. And then this 4-member group as well, right beside it, it was just not A ended with C ended with D. And then for the right matrix, there are only 2 ones present in it, so they will be grouped accordingly. So this will just be A, and then since it only occupies a single row, it will have both B and C in its min term. But since the unchanged bits for B and C are both 0, B and C will effectively be inverted. So over here in our min term, we have inverted B, inverted C. And then for its column, the unchanged literal is D. It remained in its 0 bit, therefore it will be present in our min term also. It won't be cancelled out, so it will be not D. So for output E, this is our 4 min terms right here. And then for the first 3 min terms, we can see that not A is common to all of them, so we can factor it out. Then it will just be ANDed with the ORed terms here on the inside, and it will effectively be ORed with the min term that we were able to derive from the rightmost matrix. Then moving on to F, second to the last, almost there. For our left side matrix, we only have a single group which consists of 8 members, and just like the ones prior to this, it's the same, so it will just be not A ended with not B. Then for our right matrix over here, we now have the bottom half as the one populated with all ones, so this will be one group. So since A is not effectively cancelled out, it will remain the same. And since it was able to encompass all 4 columns, it effectively cancels out D and E. Then since its unchanged literal is B and the unchanged bit is 1, B will stay as is. So this group right here, this 8-member group, is A ended with B. Then over here, we have for our last grouping, we have 4 members for it, and A is also not cancelled out because there's no other grouping similar to that here on our left matrix. For our row, the unchanged literal is C and the unchanged bit is 1, so C will remain as is. And the same could be said for its column, except the unchanged literal is D, so D will remain as is because the unchanged bit is 1. So this grouping here is A ended with C ended with D. So putting everything together, we will have this as our SOP equation, but if you look closer, these two, the first 2 min terms are actually the complement of one another. So we can simplify this to A x nor B, and then we will just OR that with our third min term over here, A ended with C ended with D. And finally, for segment G, our very last group, I will just zoom out for a bit. Okay, so for our left side matrix, we have 2 groups in total. The first being this one over here. Since this group only occupies a single row, it will have B and C in its min term. But since the unchanged bit of B and C are both 1, B and C stays the same, they won't be inverted. Then for its column, the unchanged literal is E, but its unchanged bit is 1, therefore E also stays the same. So for this one, it will be A not, because A is effectively not cancelled out. And then this will be A not ended with B ended with C ended with D. Then for its last group, for the left matrix, It also occupies a single row, so B and C will be observed in its minterm, but since the unchanged bit for them is 1, B and C won't be inverted, it will stay as is, as we can see here. Then for its column, the unchanged literal is D, and it remained at bit number 1, therefore it's gonna stay as is. So it's just gonna be not A ANDed with B ANDed with C ANDed with not D. So these are our two min terms that we were able to get from the left matrix. Then, as we can observe from our right matrix, all of the cells are actually 1. So all of it can be grouped since it's gonna be a 16-member group. So it being a 16-member group effectively cancels out literals B, C, D, and E except A, because as we saw from output B a while ago for segment B, for us to cancel A, our left matrix must also observe the same characteristic as this one. So for our SOP equation, we just put all of them together and it will just be ORed, our minterms. But then for the first two minterms, we can see that not A, B, and C are both common to those terms, therefore we can factor it out, and then we will AND it with an E ORed with D. Then A will just be ORed with this term right here. So as we can see, this is our SOP equations for our truth table that we were able to derive based on our AHI count and its corresponding 7-segment display. So now that we were able to complete all of our SOP equations per segment for the display, our groupmate, Dustin, will now implement all our derived SOP equations using Logisim in order to create our decoder.
So let's get started. So this is the truth table of our decoder, which is seen here, and this is the I count 7-segment display, and this is the output for A, B, C, D, E, F, G. So here, and this is the equations as well, C, D, E, and F. So let's start on making the circuit. So let's go with letter A. So we need inputs. Let's label them letter A. So this one is also letter B, since the output the equation that of output B is 1. So we need a constant value of 1. So let's start on letter A first. For the output A, so we need output A. after doing letter A, let's now proceed to letter B, which is the constant. We just have to put this as constant. circuit. Let us try now. 0, 0, 0, 0, 0. The only G is 0, so this is correct. Then let's try 0, 0, 0, 0, 1. So letter G is only 0. Let's try 0, 0, 0, 0, 0, 1, 0. So the output will be like this. Letter G is the one only with the 0 value. Let's try 0, 0, 0, 0, 0, 1, 1. Only letter G again is 0. And let's try 0, 0, 0, 0, 0, 0, 1, 0, 0. The output will be the same. G is only 0. Let's try 0, 0, 1, 0, 0. Let's try 0, 0, 1, 1, 1. So the same. G is only 0. Then let's try 0. Let's try 0, 1, 0, 0, 0, 0, 1, 0, 0, 0. So the B and C is only 1. That's the value of 1. So next is this one. 0, 1, 0, 0, 0, 1, 0, 0, 1. Only B and C. Let's try 0, 1, 0, 0. The same. Then 0, 1, 0, 1, 1, 0, 0, 0, 1, 1, 0, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0. So letter B and C is only open. Then let's try 0, 1, 1, 0, 1. Let's try this one, 13. 0, 1, 1, 0, 1. And these are A, B, C, D, E, F, then G. This is correct. So this is the new circuit that I've made, and I will show the truth table by using this circuit. So let's get started. So 0, 0, 0, 0, 0, the output should be 1 and letter G is only 0. A, B, C, D, E, F, G. So 0001, the same. So only letter G is 0. Then 10. 11. Then 100. 01. One 110. Then 111. Up to here. Then next is this one, then the 100 up to 01100. The only ones are B and C. So 100, only B and C are open. Only B, R, C, and open. Then next is the 1100. You can see B and C only open. So let's try 1101. So 1101, up to this on 10001, only zeros are C and F. So C and F. C and F are all close. So this is correct. Then let's try this one. C and F are close. Let's try this one. C and F are also close. Then let's try 10000. C and F again are closed. Then 1001. C and F are closed. So now here, the only zeros are E and F up until 10101. 10101. So E and F should close. And this is correct. E and F are closed. Then E and F are closed. So the rest should be A, D, E are closed or 0. A, D, E are 0. A, D, and E are 0. So A, D, E are closed. Then A, D, E are closed. A, D, E closed. And lastly 1, 1, 1, 1, 1. 0, 1, 1, 0, 0, 1, 1. So this final circuit is correct.
So now I was tasked to implement the comparator part of this project, and we will be using that for the sensor 1 and sensor 2 values as well as the threshold value. So each of these sensors will be paired to a threshold value. Just a quick review of the n-bit comparator. We have 2 inputs and 3 possible outputs, the low, the equal, and the high signal. So these are the 4 possible combinations of those 2 inputs, and as you can see, there's only 1 possible output for each of them. So this is also the most simplified Boolean expression from the lecture of Ma'am Pellegrino, so we will just be following this. And output 1 here, where it is represented by the equal signal, we will be using this as the threshold. And over here, when A is greater than B, we'll be treating this as the input for the sensor. So that is according to the given problem in project 1. So now that we already have this simple Boolean expression, we can now go to Logisim and implement our comparator. First, I will be adding a circuit and name it comparator. So in here, I will be placing 2 inputs. So the reason why I'm creating another comparator instead of just using the comparator that I have used in the previous vlog is because this is simpler and cascading is not needed. It is not needed in our project 1. So to lessen the cost, I'll be creating a new comparator na lang, which is simple. So for this comparator, I've already prepared the 3 IC that I'll be using, because according to the Boolean expression, we'll be needing the complement form of these input values, so that's an inverter. And then for the first signal, the low signal, so A naught ANDed with B. So let's go ahead and create that. A naught ANDed with B. So A naught ANDed with B, and their output should be the low signal. So let's label that low na lang. We will not be using this input, but of course we needed to complete our comparator. Here, the greater signal muna. So the greater signal naman, says that A is ANDed with B naught. A is ANDed with B naught. So A is ANDed with B naught. And their output would be the high signal. So let's label that H na lang. And then finally, we have the equal output. We'll be using a 7432 IC. So first, A is ANDed with B, and the complement of A is ANDed with the complement of B. And their outputs are ORed together. So this output value over here represents our equal signal. So I will just be labeling that as E. So we have already created our simple 1-bit magnitude comparator, and we will be setting up the first part of our project by using them for the input threshold and sensor. So there are two inputs needed, the sensor and the threshold. So we'll be labeling this as sensor 1, and then threshold. Ay, sorry, mali pa spelling. Threshold. Tama ba? Okay. And let's just copy and paste this for the second sensor. And let's just edit the label sensor 2. Okay, so the high signal will represent the first, the sensor. So it should be a greater than, kasi sabi sa problem, di ba dapat greater than or equal to. Okay? So this is the equal to. So now we will be using a built-in gate here. And we will be using the OR gate. Litan lang natin yan. Okay. Another one. So why did we use the OR gate? Because we'll be combining them using an AND gate. So lagyan na lang natin ng, pag natin lagyan ng output, we can see naman that when the wire is green, it is turned on, and when the wire is dark green, it is turned off. So we can see here that all of the sensors are turned off, as well as the threshold. So therefore, they are able to yield an equal output signal, and when they are ORed together, then they are connected to an AND gate here, so that we can implement the conditions of the problem. If we turn on either one of them lang, both of them lang, ganun din, turned on. But what if I do this? So it is against the conditions that was given to us in the problem. The threshold is greater than the sensor in this case. So therefore, there will be no signal here flowing through here, and also to the AND gate over here. So even if one threshold is also turned on, this cannot be turned on because these are OR gates. So these are OR gates, which are connected to an AND gate. So even if one of them is turned on, this will not turn on. The final output will not be turned on because they are ANDed together. And that is the definition of the condition where sensor 1 and sensor 2 are only greater than or equal to the threshold. So if all of them are turned on, then the signal will be on because they are still equal. So the same way goes for when they are all turned off, and also when sensor 1 is greater. So we have proven that sensor 1 is greater over here because we have used the comparator, the simple 1-bit magnitude comparator. So this concludes my part for project 1, and the next presenter will be Sienna once again for the other component.
Now that we were able to build our comparator as seen by what Matt was able to do, its output will actually be fed into an incrementer as an input. So after we were able to build our comparator, we will now build our incrementer using a full adder, 5 full adders to be exact. And once we were able to create one adder, we multiply that by 5. So therefore, once we have 5 full adders, that will inherently create our 5-bit incrementor. Since our incrementor will be comprised of 5 full adders, we first must know how to create a single full adder. So here on our screen, we can observe the truth table for a full adder, which has A, B, and carry in as its inputs, and sum and carry out as its outputs. So what the full adder does is that it basically just adds, as imposed by its name, adder. It adds A to B respectively, as well as the carry in. So as you can see here, if we were to add 0 to 0, we still have 0. And if we were to add 0 to 0, our sum would be 0. And since we didn't necessarily carry any number, our carry out will remain as 0. Then here, for the second row, we still have 0 plus 0, it's still 0. But now, if we add 0 to 1, our sum will now be 1, just like if we were to add it vertically, right? 0 and then 1. So over here in our line, it will sum as 1. And since we did not carry anything over, our carry out is still 0. And the same could be said for our third row. It will just be 0 plus 1, it's still 1. Then 1 plus 0 is still 1 with no carry out. But then on our fourth row, as we can see here, if it's going to be a binary adding, normally if this was decimal, it would just be 2, right? 1 plus 1 is 2. But for a binary number, it would be 1 and 1. Its sum would be 0, and then the 1 will be carried over to the next bit. Therefore, our sum is 0 and our carry out is 1. Then for the next row, it is just going to be 1 added by 2 more zeros. Therefore, its sum is still 1 and the carry out is 0. But then as you can see here, for the next row and the row after that, just like the one that we've had on this row, it will be 2 1s added together. So its sum again will be 0 and its carry out will be 1. And then lastly, for the final row, so we would have 1, right? 2 1s. 1 plus 1, that's going to be 0. But then you're going to add another 1. So its sum will be 1. But since here we added these two, there was a carry, right? So a carry will be 1 over here. So the ones marked by yellow and blue just like any other truth table that we were able to experience prior to this, we will map out the ones in our truth table, or just basically get our minterm from the rows that has a 1. So our truth table will be divided into two, one for the sum and one for the carry out. So let us first look at the sum. It is the one marked by yellow over here. So as we can see here, in its row, it has A, B, and then carry in as 1, but then A and B are both 0. So if we were going to get the sum of products, both A and B will be complemented while carry in will stay as is, CIN. So we will just AND all of this, so it's going to equal to our first minterm here on our sum here below the truth table. So it will be not A ANDed with not B ANDed with carry in. This stands for carry, the C, then in. Then it will be ORed with the next minterm that we marked yellow here, but this time it is A and carry in that are 0, so they will be complemented as seen here in our minterm. And then next, it is now B and carry in that are marked 0, therefore they will also be inverted. So as we can see on our third minterm here in our sum, they are marked. And then lastly, for the fourth minterm that we were able to mark yellow, A, B, and carry in are all 1, so they stay as is. So this was our sum of products for our sum. But as we can see, we can actually further simplify it. So based on the first two minterms, we were able to factor out A naught because it is common to both minterms. And then next, for the third and the fourth minterms, we were able to factor out A because it's common to both minterms. But now that we were able to simplify this, if we look even further, they could actually still be simplified more. So our B naught ended with C, sin, or carry in, or with B ended with not sin. These two are actually, they could be exclusive ORed together, because for B here, they're complement, and then the sin are complement. And then here, B not ended with C not, or with B and sin as is. They're actually also the whole entire thing are complements of each other, so they could be XNORed. And then A not and then A here, they could be inverted. So for this, they could be all simplified to A X or B X or C. Then if we wanted to do the truth table method instead, this is how it would look like. So as you can see, the pattern is as if it was jumping, right? Every row, and there was no adjacent ones to each other. They're all as is. So if we see this kind of pattern, it will be A, our literals will be XORed with one another. So A XOR B XOR C or sin. And then lastly, for our carry out, we just do the exact same thing. We would have to look at the ones marked with 1, or here we marked it with blue so that we can observe it more easily. So the ones marked with blue are the ones that has a 1, right? So that is what we convert here on our truth table. So the very first group, it would just be group 2 for each because there's no adjacent force. So as we can see here, our 1 over here down below, it will just be A. And since B was able to change and sin was the only literal that did not change, and then its unchanged bit is 1, sin will stay as is, so that is our third minterm over here. So it's just gonna be A ended with sin. or carry in. And then for this one, we can see that A was able to change, right? And since it only occupies a single column, it will have both B and sin as its min term. And since the unchanged bit for the literals are just 1, it will stay as is. And then lastly, for this group, since it only stayed in a single row, it will definitely have A in its min term. And then for its column, we can see that the unchanged literal is still B, and C was able to change from 1 to 0, so it will be A ended with B. So for our carry out sum of products, this is what we have. So basically, this is what our full adder will be composed of. So our full adder for its sum, this is a single output for it. It will just be A XOR B XOR C. And then for our carry out, it will be B ANDed with sin, ORed with A ANDed with sin, plus or ORed with A ANDed with B. So this is our full adder that we will create on Logisim, and we will, once we've created a single full adder, we will just multiply that 5 times, and then we will finally be able to create our 5-bit incrementer. So now let us go to Logisim. I will just minimize this first so we can still see our SOP equations, and I will just put it down here. So we will first do A XOR B XOR C, which will be our output for the sum. So we would just have to get our 3 inputs. This will be A. Then we will just copy that. And then the second one will be B. Then the final one would be our carry in. Oops. Okay. Then we will just get our XOR IC here, or 746 IC. And then A and B will first serve as the first 2 input. So A and B are the first 2 inputs for the first XOR gate. Then their output will serve as the first input for the next XOR gate, and the carry in will serve as the second input for the second XOR gate. Then that output is already our output for the sum. So we just got an output here at the top, and we will label this as sum. Okay, so now that we are able to create our output for the sum, let's do the carry out. So the first thing we're going to do is be ANDed with carry in. So we will just get an AND gate here, and then we will do B ANDed with the carry in, and then their output will go to an OR gate, or IC, as its first input. And then next we have A ANDed with our carry in. So that's A ANDed with the carry in. Then their output will serve as the second input of our first OR gate. Then their output will serve as the first input for the second OR gate. I apologize for that. Okay. And lastly, we have A ANDed with B. So that will be A ANDed with B. Then their output will serve as the second and final input of the second OR gate. And then their output will finally be the output for the carry in. So we'll just copy this and then label it as carry in. Carry out rather. So this is basically our circuit for a single full adder. So the next thing we're going to do is create basically 5 of these circuits in order to create our 5-bit incrementer, as you can see here on our left panel. So now we might find ourselves asking, how could we create an incrementer, a 5-bit incrementer to be exact, with the full adder that we just created? So let me pull up our Excel file again. Going here over to our right side, we can see here in our screen actually a 4-bit incrementer, but we must do 5. So right, for our full adder from a while ago, we had 3 inputs in total, A, B, and carry in, and then we had an output of sum and carry out. So as you can see here, for the very first bit, or the least significant bit of our incrementer, so we will have an output A and B as is, but for its carry in, it should have an input of 0. So for our first full adder in our incrementer, for the least significant bit, its carry in must be grounded for it to be 0. Then its sum will just be observed as an output. Then its carry out will go as a carry in for the next bit that will be a full adder also. And this goes on until our last 5th and most significant bit. But then for our 5th and most significant bit, for its full adder, its carry out will not have any kind of it won't have any outputs. It will just stay as is. So again, I will just put this here at the bottom. I'll minimize it first so we can still see it as a reference. So the first thing we're gonna do is get an input. This will be A. So since we would have both A and B, right, we should label this. But first, before labeling, let's make it face south. So this will be our least significant bit, because we would want our incrementer to be read from left to right. So our least significant bit should be situated from our leftmost, and then for our output, we would want our least significant bit to be the one in the lowest, so that we can read it from south to north. So since this is A and the very first one, we will label this as 1A, but we will make the label in the north. So for this is 1A, then we will just get our full adder here, and then we will connect our 1A to our first adder, full adder. Then now we will get our B input, but this time we will make it face north. That will face north, and then its label will face south. Then since this is our first input for B, we will label this as 1B. Then we will also connect it to its respective input. Let's just line it up with A. Oops. There. And then based on our diagram, its carry in will be 0. Therefore, we will ground it. So we will just ground this. Let's go to the wiring and go to ground, and we will just effectively ground that. And then we will have our very first output for the sum, which we will label as 1. Okay, this will be output 1. So this will be 1. And then based on our diagram, right, its carry out will go to the carry in of the second full adder. So let's just get our second full adder. This, by the way, our first adder here is our least significant bit. So are the two outputs here. So this is our second. Its carry out will go to the carry in. Okay, then we will just create our next inputs. This will be 2A, and then this will be 2B. We will connect it respectively. Okay, and then this will be output number 2. And then our next adder for our third bit, again, the carry out will go to the carry in of the next one. And then now we will have our third input for A. We will just name this as 3A, then 3B respectively. Apologize, sorry. The wiring. There. So this will be 3B. So I'll just connect this to A and then B. Then this will be our third output. And we will just label this as 3. Then for our fourth one, we'll get another adder, and then I will just adjust our outputs. And then again, its carry out will serve as the input for our carry in. Then we just create another set of inputs for both A and B and label them 4A and 4B respectively. This will be 4B. Then we just connect it. This one's for A, and this one's for B. Then this will be output number 4. Then again, we just adjust our outputs. Then for our fifth and final and most significant bit, the last full adder will be added. Then we just create again 5A and 5B outputs respectively. 5A. And this will be 5B. And we just connect it here for A and B. Sorry, this was supposed to be 4. And then this will be our fifth and final output. We will label this as 5. So there you have it. This is already our 5-bit incrementer. This is our 5-bit incrementer for our main project, and it is composed of 5 full adders to be exact. So when you will connect this to our main project, we will be reading our binary from left to right. So this is our least significant bit, and then when we read the output, once we connect this to our decoder, this will serve as the least significant bit. And then here on our outputs in B, our comparator will be connected to the least significant bit, while 5, 4, 3, and 2 will all be grounded. So that is it for our incrementer. I will now pass this on to my next member, who will be creating now our decoder. Thank you.
Ayan, so sa 12, so yung input mo is 12, tapos yung hindi satisfied yung condition, and then pag satisfy yung condition. So pag nag-13 yan, magiging 2. Magiging 3 pala.
Okay.
Ang 13 is 01101.
Okay, so this is
Wait. 12 lang siya, 12. So 1100, 1100. Ano daw? 01100. 01100. Tapos yung sensor mo, mas mataas yung threshold. Yan. Kasi ibig sabihin, hindi siya mag-i-increment, di ba?
yes, ma'am.
1 pa rin. So this time, gawin mong equal yung sensor. 1, 1. So dapat mag-i-increment. Oh, dapat magiging 2 yan.
Tapos
Naging 2 na po, ma'am.
Okay. Sige.
From
1 kanina. Sige. So tapos yung susunod na range, ano yung last item?
30.
17.
Ay, 7.
17.
17. So yung 17, hindi satisfied yung condition, so dapat 2 pa rin yan. Tapos sa 0 mo yung sensor. 0 yung sensor, tapos 17. So 10001. Yan.
2 po.
So 2 pa rin. This time, yung sensor naman, gawin mo 1. So dapat maging 3 yan.
Yes, ma'am.
So
Gumana
kung
naman.
17, maging ganun.
up po.
Yung next range,
21 po.
21 po.
1.
What is 21?
21 10101 21.
16,
Ay, pag naka-off pala, sorry po. Hindi ko na-turn off. Ayan po.
so 3 pa rin. So then, pag same na yung sensor,
Okay.
4.
Last pa yung 32. Yan po, pagka 32 na
wait,
naka-off po.
hindi yan 32, 31 yan.
Ay, 31 po pala. 5 bit lang pala. Sorry, ma'am. 31 lang pala.
So, for our conclusion po, ma'am, for each part of our circuit po, isang comparator, isang incrementer, then decoder, we were able to give each member a single part po. So, equal naman po yung hatian namin when it comes to the work done for the project. And then, based on here po, we were able to, number 1, implement the week number 3 na okay, commercial break.
Yes.
Okay. Okay. Tapos na commercial. Susunod. Okay, number 1, we were able to implement po yung comparator, number 1, then incrementer circuit that we were able to build po for week 3. Tapos decoder naman po based on what we were able to build on week 5. Then when it comes to the challenges naman po, ma'am, I think yung pinaka biggest challenge namin was through the decoder kasi when we were able to create truth table po namin, nung nag-K-mapping na po, since 5 variables, medyo marami. So, yung ginamit po naming variable map, yung dalawang 2x2 na matrix, yung isa A is equal to 0, tapos yung isa naman A is equal to 1. So, since marami po yung parang cells, medyo naduduling po kami, kaya we had to repeat our process twice lang. Pero once we were able to check everything, na-implement naman po namin si decoder on Logisim, even though the time we did it was quite lengthy. We were able to do it naman po. And once we were able to build the whole circuit, another challenge that happened was yung pagko-connect lang naman po for the project, starting from the comparator up to the 7-segment display. Medyo nalito lang po kami kung ano yung yung least significant and then the most significant bit. But after we were able to overcome that naman po, we saw that everything was able to work naman in the end. So we were able to create our project using our previous lab activities po.
Okay, so comment ko lang, paki-label yung mga ICs nyo.
Yes,
Kung
ma'am.
unlabeled. Okay.
Yes, ma'am.
Sige, yun lang. Bye-bye. Thank you.